In this question, we have lots of penguins of three different types: emperors, kings, and gentoo. But from now on, I'm going to refer to them just as E, K, and G for simplicity. And we have this shuffle that they can perform. And we have to move them into a certain order. We have to get all the emperors to the left, all the kings to the right. And there are so many penguins, 2,025 of them, it's not obvious at first what to do. So let's consider a simpler situation. The simplest possible situation is where there are just 3 penguins. So let's consider that first. One of which has an E, another a K, and the last a G. And with just 3 penguins, the only thing we can do is to apply this one shuffle over and over again. So let's see what happens. If we apply it once, the E moves to here, the K moves to here, and the G moves to here. And we have another permutation of the penguins. Apply it once more. The E moves to here, the K moves to here, and the G moves to here. Another permutation of the penguins. And if we apply it one more time, something unusual happens. The E will move to take the K's place. The K will move to here. And the G will move to here. And the penguins will all be in the exact same places that they started out. So what this situation tells us is that there is no point applying any given shuffle 3 or more times. It would be equivalent to applying it once or twice or no times at all. Let's now consider the next simplest possible situation with 4 penguins. So we'll add in a second G and we'll label our 2 Gs G1 and G2. So now, at each move, we have one of 2 shuffles we could apply. We could apply the shuffle with G1 or the shuffle with G2. And remembering from our previous observation that there is no point applying any single shuffle more than twice in a row, there's not that much we can do. So we can play around with applying different shuffles in different orders, and we discover the following sequence. So let's first of all apply the shuffle involving G1. So the E will move to here, the K will move to here, the G1 moves to here, and the G2 stays where it is. Now, let's apply the shuffle involving G2. The E will move to here, the K will move to here, the G2 moves to here, and this time the G1 stays where it is. We do this once more. And now we apply one final shuffle, the shuffle involving G1. And we observe that something special has happened. If we compare the final positions to the initial positions, we see the E and the K have swapped, and also the 2 Gs have swapped. But in this question, the penguins do not have an identity. Only their type matters. So this is equivalent to just swapping the E and the K. So using the sequence of 4 moves that we just saw, we can swap any E with any K, whilst also swapping 2 Gs, but that will leave the pattern of types of penguins unchanged. And similarly, because there's symmetry between the 3 kinds of penguin, we can swap any E with any G, and we can swap any G with any K. And now it is clear to see how to get all of the E's on the left and all of the K's in the middle and all of the G's on the right. So suppose these are our 2025 penguins. And consider the first 675 of them. If there's any penguin in here that is not an E, then there must be a penguin somewhere in the remaining slots that is an E. And in fact, the number of penguins in the first 675 slots that aren't E's must equal the number of penguins in the remaining slots that are E's. So we compare these up and swap them, and we will find ourselves with all of the E's on the left. And now we consider the next 675 slots, and we can do exactly the same thing. If there is any penguin here that is not a K, which means, of course, it must be a G, then there must be a penguin here that is a K. And we compare up these mismatches and swap them, put all of the K's in the middle and all of the G's on the right, and we are done.